Okay, so today we're going to be doing worksheet number 8. We can start with the first one. In each of the following cases, circle which reaction would occur faster. Just by looking at all of the alkyl halides, you can see that they're primary, and so we're probably going to be favoring SN2 or E2, but in this situation, I believe we're just going to be doing substitution, so SN2 is what we're focusing on. The only thing that changes between these two pairs, or this pair right here, is the nucleophile, and they're both considered strong just because they have the charge on them, but which one is stronger? And so you can do it based off of acidity and basicity of the conjugate base, or you can focus on if the lone pair is able to resonate or not. If the lone pair is able to resonate like how it is over here, then the electrons are distracted and they're not wanting to attack anything. They're pretty stable. Whereas over here, we have the electrons pretty focused on oxygen and there's nothing taking these electrons away. And so this would be our favored reaction, or the faster reaction. Between these two, again, the only thing that changes is the nucleophile. So you have, between nitrogen and oxygen is really what we're dealing with. And so on the periodic table, you have this right here. So NOF, and then freaking Claire brought ice. And this is pretty much like the tip top of the periodic table. Periodic table is like this region right here. Fluorine is your most electronegative. Going up and to the left, you have a better base, which is usually interchangeable with nucleophile when you're just talking about their strength, not when you're talking about their abilities. So that's the trend for better base and better nucleophile. And just as a side note, the opposite, going the other way. So I'll do another color. Going right and down is a worse leaving group. But we can forget about that for this question. So between the better base of nitrogen and oxygen, we would pick nitrogen because of the periodic trend, so that electrons are more available when they are more to the left of the periodic table. And that's just because when you go to the right of the periodic table, you have the more electronegative atoms that love to keep their electrons to themselves. And so this one right here would be your answer. Okay, we'll do the next one. Only thing that changes here is the leaving group, and so you're between bromine and chlorine. So here you would concentrate on the trend that we wrote in it initially. The better leaving group is going to be bromine. And that's just because bromine can handle that negative charge throughout its bigger electron cloud. Okay. Then we'll go to number 2. These were supposed to be substitution reactions as well, so I added this to each one of them. Assuming the overall reaction is endothermic. Endothermic means product is greater than reactants in terms of energy. Draw an energy diagram, label the axes. So let's just start because there's going to be a lot of labeling to do. I'm going to go over here. It's substitution, I just need to know which one, and then based on the nucleophile, it's a strong nucleophile, so it's SN2. And so this should be a one-step reaction, and the product energy has to be greater than the reactant energy. So it'll be like that. Okay, we drew the energy diagram. Let's label the axes. So on the y-axis we have energy, on the x-axis we have reaction coordinate. Alright, so this is good. This is the reactants over here, this is the product over here. Activation energy is the amount of energy that you need to overcome for you to get to your products, and so you need to overcome all of this energy right here, starting from the energy of your reactants to the energy of the transition state, and that's your activation energy. So we're done with this one. Transition state is this tip top over here. And enthalpy change is the difference between products and reactants. There can be a lot of enthalpies in a reaction if you have like a multi-step reaction, but for this one it's one step, so you have delta H overall. Draw the structure of the transition state. So it's SN2. We're just gonna want to draw our things, our leaving group and our nucleophile going in opposite directions of each other. So we'll do like iodine coming over here, breaking off, while your nucleophile comes in and attacks. And we'll bracket that. Okay. And then the last thing we have to do is put their partial charges. So when iodine leaves, it's going to have a partial negative charge. The nucleophile is a partial negative charge, and it's attacking a partial positive charge. So that's your transition state right there. And now we need to provide a mechanism for the formation of the product. And this one shouldn't be too bad, just because, again, it's a one-step reaction. So we should just draw multiple arrows. So put the electrons in your nucleophile, identify your electrophile, which is this carbon right here. And so draw, starting from your electrons to the electrophile, and point at the carbon electrophile. It's a one-step reaction. When you make a bond, you have to break a bond, so leaving group leaves. I'm not showing you stereochemistry in the initial product, so like over here. So then you won't need to do that right over here, because you would usually do a backside attack, but I'm not telling you which side is the front, so this would be enough. Okay, we'll do this next one. Number 3, assuming the overall reaction is exothermic, which means products is less in energy than the reactants. John energy diagram, labeled axes, reactants, products, and activation energy, and so on. So let's just start drawing the energy diagram. So energy on the y-axis, reaction coordinate on the x. So this, we need to identify whether this is SN1 or SN2 so that we know how many steps there's going to be. This looks like it's going to be SN1 since we have a weak nucleophile. And so this should be a 2-step reaction. If they were to make you do this on the test, which you most likely are, he'll probably give you an idea of which one is going to be your rate determining step. Since I didn't give you anything, I'm just going to make one up right now for us. Let's say that our rate determining step is step 1. So when the leaving group leaves. And then I will say, let's see. So exothermic. Let's do A, B, and C. C being your product, A being your reactant. Your product has to be less in energy than everything else, so I'll do this right here. Okay. So I'm starting off, that should be A. B is intermediate in energy. Another hump, and then C should be last in energy. So this should be about right. And it's drawn slanted, so sorry about that. Okay. We'll do this as A, the intermediate is B, and then my product is C. And let me check that all the energies are right. A is highest, B is intermediate, C is lowest. Okay, looks good. And then step 1 is our rate determining step. Okay. Label reactants. So if it's asking you to label reactants, drawing A is not enough, so you can spell it out, put reactants and products, but I'm going to put R and P. Activation energy, so it's the same thing, difference between the start of a reaction all the way to its transition state. And so this right here is your activation energy, the energy needed to overcome in order to go to your product. So in this case, A is our reactant and then B is our product. Then you move to B, and so B we would consider a reactant, and C is our product. So how much energy do I need to get from B to C? And it's you need to overcome this amount of energy. So EA1 and EA2. Then you have your transition state. So this one can be transition state 1. This one can be transition state 2. Then you have your enthalpy change. Since this is a multi-step reaction, you're gonna have like three change in enthalpies, so let's label those. Enthalpy is usually, again, products minus reactants, but here you have different products and different reactants. So from A to B, A is my reactant and B would be considered my product. The difference between these is my delta H number 1 for the first step. Then I go to B. B is considered my reactants and C is considered my products. And so draw the difference between these. And this is your delta H2. And then finally, you're gonna have to do the delta H overall. Let me do that in a different color, which is going to be your reactants minus your final product. And so this right here, let me just draw my this would be your delta H overall. Okay. Next we have to draw the structure of the transition states. So let's do that. Resize. I'll put it right here. So transition state number 1 is when, actually, yeah, we'll do transition state number 1. So transition state number 1 is when your leaving group is leaving. And so I will draw my initial structure. And I will draw a dotted line to iodine showing that it's kind of breaking off. And then I'll put the partial positive and negative signs. Let me just see where. So when iodine leaves, it's partially negative, and then it'll leave my carbocation, which right now is partially positive. I will label the intermediate as well, in case they ask that. Intermediate. In this question, they didn't ask for it, but just so that we have it. And the intermediate is usually always going to be just your carbocation, which is also B in the energy diagram that we wrote out. Then we have transition state number 2. So write that in brackets. It's the nucleophile attacking, and so what you'll do is you'll draw another dotted line from your nucleophilic part of your compound, which is going to be your oxygen, and then you can write everything else out. But it has to be, you have to be showing this dotted line to oxygen because that's the one that's going to be attacking. And so you can put your partial, I'm going to close it really quick, put your partial negatives and positives. This is your partial negative, put it next to the oxygen, and this is your partial positive that you're attacking right here. Okay, so we're done with those. Last step is to provide a mechanism for the formation of the product. So let's do that. Let me do it in blue. Okay, so step number 1 for all the ones, E1 and E2, or SN1, is leaving group always leaves. And so show that bond breaking and your carbocation intermediate. Step 2 is ETOH attacking from the electrons on oxygen. And you can write these in straight lines so far, but you are gonna need to write a wedge and a dash in the last portion because you created a stereogenic center. So let's do that. I'm going to draw the ET part as its actual carbon. And oxygen has 3 bonds, which it doesn't like, so it has a plus charge. Iodine had left previously, so you can draw iodine again to go steal the hydrogen and break that bond and put the electrons on oxygen to neutralize it. I've seen people use just another ETOH, which is totally fine because you have lots and lots of ETOH in your solution, so that can go and take the proton as well. Or you can just go back to iodine, whatever you'd like. But then in the final product, I'm going to write this right here and this right here. Okay, so again, the only reason that I started drawing this right here is because we know that in an SN1 reaction, you attack from the front and the back. If there is a stereogenic center, you kind of want to show that you know you're going to make a racemic mixture like this right here. And so we created a stereogenic center. Initially, we had one as well, but I didn't show it to you, so it shouldn't matter too much. But I mean, same things apply for the mechanism. But you're pretty much always going to have to show front and back attack on your final products for SN1 if they create a stereogenic center. For over here, though, I didn't tell you what was front or what was back for the iodine, so you can just keep it as a stick, so that'll be fine. Okay, last one. So draw the structure for the following polar aprotic solvents. Just remember, protic means you have a proton, pretty much like on an electronegative atom. You won't see a proton on an electronegative atom over here because they're polar aprotic solvents. I don't believe you have to know the name like spelled out, but you do need to know the structures because those are going to be easy points in the exam. If you do know the names, they're going to be kind of easy to solve anyways. So like dimethyl formamide. So form means that it's like an aldehyde on one side and then you have something else on the other side. Amide means that you have this functional group right here, a carbonyl attached to nitrogen, and then dimethyl just means the 2 methyl groups. So if you know the names, it'll help, but you won't need to as long as you know the structures. Okay, make sure to email me if you catch any errors in what I wrote or if you have any questions.